Welcome back to Virtual Physical Science. This is Energy Part 5. Alright, so another example of energy conversion and conservation. We have a little box, something heavy, maybe it's a piece of lead, and it's attached to a spring, something that can stretch and compress. Okay? And so this is supposed to be a cartoon. I pull this thing down, I hold it here for a second, and then I let go. And when I let go, this thing is going to shoot up and then fall back down. Okay? My spring is the kind of spring that at these positions, here and here, the spring is what we call relaxed. It's not stretched and it's not compressed. That means that there's no elastic potential energy stored in it. Okay. So what I want to do is I want to walk through each of these 5 frames in our cartoon and think about what kinds of energy there are. Now, here in frame 1, I pull the mass down, and just before I let it go, how much kinetic energy does it have? How fast is it moving? That's right, it's not. So it has 0 joules of kinetic energy. Now, I'll tell you that it's a certain distance above the ground, and so let's say that it has 5 joules of gravitational potential energy, GPE, 5 joules. EPE here doesn't stand for electric potential energy, it stands for elastic potential energy because the spring is stretched. And I'll tell you that it has 20 joules of elastic potential energy. So altogether, how much energy is there? That's right, 25 joules. Okay, so now we let this thing go. It flies up to here. I told you that here it has no elastic potential energy, right? Because here and here the spring is relaxed, not stretched, not squished. So EPE, 0. In both of those places. Alright, now let's say that the GPE has increased because it's gone up, it can now fall farther. Let's say the GPE is 10 joules. How much kinetic energy must there be? If there was 25 joules to begin with, there must be 25 joules here. 10 here, 0 here, there must be 15 joules of kinetic energy. Alright. Well, that makes sense because when we let this thing go, it's going to be moving. Here, it wasn't moving, so it had no kinetic energy. But once we let it go, it's going to move, and it turns out that it's going to move really fast at this point. So it's going to have 15 joules of KE. Alright. Then we get up to the top, the highest it's going to go. Right, and this thing is going to stop temporarily when it gets to that highest point. So how much kinetic energy does it have if it's stopped? Right, 0. Well, what about EPE? Let's say that it stores 10 joules of potential energy in the elastic squishing of that spring. Then how much gravitational potential energy must it have? Yeah, this math is easy. 15. Okay? We still add to 25. 25, 25, 25. So we're sloshing energy around from one place to another, but the total amount is staying constant. It is conserved. Okay, and that's what conservation of energy is all about. Right? Conservation of energy is about the total amount of energy not increasing or decreasing. I'm going to stop there. Now, if that was absolutely right, then this spring could just bounce up and down forever. But we know that eventually it'll stop. And that has to do with friction. And we're going to get to that in just a minute. But first, I just want to show you a quick movie that helps to illustrate the point I'm trying to make. So check it out. So you saw the little box on the spring bouncing up and down just like we were talking about. Now you might want to go back and look at it again and check out how those graphs of potential, and in that graph, their potential energy graph includes gravitational and elastic potential added together. But you can watch the potential energy go up and down, and you can watch the kinetic energy go up and down. But in the third graph, when they add them together, it's constant, it's flat, it doesn't change. So although one is changing one way and the other is changing the other way, the total somehow stays the same. And that's what conservation of energy is all about. Now, as I mentioned, because of friction, energy doesn't just slosh around between those three forms. Some energy is lost to friction. Now, we know energy doesn't get lost, doesn't get destroyed. It's a law of the universe. Energy is not destroyed. So what energy being lost to friction really means is that some energy is transferred to the kinetic energy of atoms and molecules. Heat, maybe sound, okay? And that energy is very difficult to use once it transfers to those small-scale things. So the energy is no longer very useful to us, but it still exists. It's just changed into other forms. And this is why things slow down. If you don't pedal your bike, eventually you're going to stop because of friction. And if you bounce a spring like that, after a while, it's going to stop. One last word on energy. I mentioned this once before. Einstein's famous equation relating mass and energy. And I said that c squared was really big. So I just wanted to be a little bit more precise about what I mean when I say really big. C squared is about 10 to the 17th in metric units. That means 1 kilogram of mass contains 10 to the 17th joules of energy. That's a lot. Okay, so like I said, that's enough to cause a huge amount of devastation if it were just released. Fortunately, that's very hard to do. And you can kind of think of mass as sort of frozen energy. And energy is kind of like evaporated mass. It's almost a relationship like that. All right, well, your next homework assignment is to read section 4.2 and answer on page 115, numbers 1 through 6. Okay, so stay tuned to Blackboard and email and YouTube, and I'll see you guys later. Have a great weekend. Bye-bye.